So in geology, will sometimes hear people talk about so-called hydrostatic or lithostatic pressure, and we're just going to briefly explain what those mean. A hydrostatic pressure comes from the idea that we have pressure that is equal in all directions, and that would happen if you are submerged underwater. So let's say this is us down here, and we're in a swimming pool. Let's say that's the bottom of the pool, and this is the top, the surface of the water. So we're surrounded by water. If you look at some infinitesimally small point, let's forget about an object that's as large as us, because that's a little bit too large. If you have an infinitesimally small point, the pressure in this direction and that direction and this direction and that direction, that'll all be equal. And if those pressures are all equal, then we have a so-called hydrostatic pressure, and the hydro comes from the fact that water has no shear strength. So it is not able to sustain a pressure that's different in one direction or another. For example, how would we have a non-hydrostatic pressure? Let's say you could pile up the water so that it was heavier over, that we had a thicker layer of water over here and then a thinner layer of water over here. What if you could manage to pile the water up and have the water stay that way, to stay piled up? Then the pressure here would be greater than the pressure here. But of course, if you fill up a bathtub or a sink and try piling up water on one side, it won't stay. It'll go back to its original flat surface pretty quickly. And the reason why is because water has no shear strength. It cannot maintain a shear stress that's required to allow it to have different kinds of pressures. In effect, we can't pile it up on one side of the tub or the sink. And so because of that, hydrostatic pressure always means that pressure, when we calculate it using rho GH, is a scalar. We can use a single number, a single value, to express what the pressure is under these so-called hydrostatic conditions. What is lithostatic pressure? It's basically the same idea, except instead of being buried by water, we're buried by rock. But it is the case when we can talk about pressure as a so-called scalar quantity, and we can express it as a single value. Well, what if it's not a single value? When is it not a scalar? Well, rock can be piled up, and if you had, let's say, a large mountain range here, and then you want to look at some fixed depth, let's say it's 10 kilometers below sea level. So maybe we can put that in a different color. We can have sea level here, and that should be a perfectly horizontal line. So we have a mountain that's sitting above the ocean, and there's the ocean surface right there. So if we have a fixed depth that is 10 kilometers below sea level, so here's 10 kilometers, and then here is 10 kilometers, the pressure could be very different, let's say in this case here, because over here, let's call this position 1, and then we'll call this position 2. The weight over here at a depth of 10 kilometers is determined only by the weight of, let's say we've got a sedimentary basin here that's sitting right at sea level. So we're buried by rock. But here we're buried by a lot more rock. Let's say the height of the mountain here is 3 kilometers. So if all of this material here is the same density, let's just say it's 2.7 grams per cubic centimeter for all of this stuff here, we're going to have a much greater pressure here because we have a much thicker column of rock at this depth of 10 kilometers. Rocks are strong enough that they can support a shear strength. This mountain may eventually collapse. We could have landslides or material sort of being eroded into the valley. So not just pure erosional processes, but there can be an absolute weakness of the rock that will cause it to collapse and maybe fill in a basin over here or fill in a basin over here. But it can withstand some shear strength, and so we could have a difference in pressures. In this case, it would be non-lithostatic or non-hydrostatic. If we take an infinitesimally small point, let's say we have a point that is here, then the pressure pushing from this direction could be a little bit greater than the pressure pushing from this direction. The reason why is that over here we have material that's buried to a greater depth than material over here. So in that case, we can't use a single value for the pressure. In fact, we won't really talk about pressure at all. What we would talk about is stress, and we can set up a matrix. So a matrix would be where we would consider stress in 3 directions. So we can consider it in a vertical Z, let's say a horizontal X, and a front to back Y direction. And so those 3 values can go into a matrix. If we had a hydrostatic case, then X, Y, and Z, let's draw that a little bit better. We'd have a Z, an X, and a Y. So Z is top to bottom, X is left to right, and Y is front to back. So that's what's exerting pressure on that point. So we can have X, Y, and Z. If all of those pressures or stresses are equal to one another, then we would have a matrix like this, where the diagonal matrix everything is equal on that diagonal, and then zeros everywhere else. But if the pressures were a little bit different, pushing in one direction versus another, then along that X direction, instead of 0, maybe this would be, 1.2 or something, maybe a greater pressure than this. Doesn't matter what it is. The diagonals would no longer be equal, and then the off diagonals would be something maybe different from 0. And we're not going to worry too much about this, but otherwise the fancy name for this is a tensor, and that is to contrast with the single value pressure that we will mostly deal with in petrology, referred to as a scalar.